All right, we've made it to the second day of lines in chapter 8. So yesterday we looked a lot at lines in 2 dimensions, and today we want to try and expand that to lines in 3 dimensions. So what we looked at yesterday was the idea that we could write a line using vectors. We said in 2 dimensions it worked. It wasn't really that helpful, but it worked. In 3 dimensions it becomes the only way to make it work. So there's no choice anymore. To start off, I mean, the basic idea doesn't change much, and I sort of mentioned that or hinted at it at the end of the lesson last time. If we want to add in a 3rd dimension, all we're doing is adding in a 3rd component. So here's a line. It's a vector equation of a line. We still have an initial point, and we still have a direction vector. Now this becomes really tricky to picture. So if you guys were actually here in front of me, I would have held up my fancy 3D grid, and I would have tried to show you where the point 1, 2, 3 is, and maybe you can picture that a little bit in your head. 1, 2, 3 isn't too bad because it's in that front, right, top octant, right? So it's not too bad. And then the direction vector 2, 1, minus 1. So that means go out 2 on the x-axis, go out 1 on the y-axis, and go down 1 on the z-axis. And that's the direction you should follow. And as soon as you start doing that, it becomes a lot more difficult to picture where this line should go. You can do it, right? You can do it, but it's a bit of an exercise to try and see it in your head. That's okay for us because we don't have to draw it, right? That's not the question. We are going to do some calculations with it, so we need to at least understand what we're considering, but the drawing aspect isn't going to come into play. So consider that line, and it says write the parametric equations for it. So remember our parametric equations, I was saying were much more helpful for calculations, and that's still true here. So what we're going to do is we're going to take our parameters and break it up into pieces. So we've got our x component, which will be 1 plus 2t, our y component, which is 2 plus t, and our z component, which is 3 minus t. And that doesn't look real helpful. I mean, the biggest problem is we've now got 3 equations, we've got 4 variables, so there's an awful lot to deal with. But we'll manage okay. Skip ahead here. Here's part B. Determine the point on the line that corresponds to t equals 3. This is a good example of where you could use either of the equations. You could use the parametric if you wanted to, or you could use the vector. I think I'm going to write the vector equation down because it'll actually just save a little bit of space. Parametric will work great too, though. We're subbing in 3. Whoops. And remember, we're using square brackets because this is called our vector equation. We're using vectors. We're using the vectors to tell us what point we'll end up at. So our answer here is 7, 5, 0. So it's saying to get to a point on the line, you'd end up traveling along the vector 7, 5, 0, and then the point we'd end up at is actually 7, 5, 0. Now, honestly, I'm not going to be too concerned when you finish this if you've left it as square brackets or round brackets. I do want you to keep in mind there is a difference. Right? The square brackets mean a vector, but it means we're ending up at the point 750 in the end. So just keep in mind there is a distinction. Determine if the point 15, 9, minus 6 is actually on the line or not. Well, this is one where we need the parametric equations. We have to have the parametric equations this time, so I'll put those back in. It was 1 plus 2t. Y was 2 plus t. And what we want to do is we're checking to see if these values can actually work. Is it possible to pick a value for t, and then when we sub that t in, get a 15 for x, and get a 9 for y, and get a minus 6 for z? So what we do is we sub in the appropriate values, 15 here, 9 here, and minus 6 here. And we have to solve all 3 of these for t, and what you're hoping for is that you're going to get the same value each time. So I get 7 equals t for this one. So if t is 7, then you're going to get an x value of 15. That's what that tells you. And that worked for this one too. 7 equals t. So not only that, if t is 7, then we're also going to get a y value of 9. So if t is 7, we get the 15 and we get the 9. And this one, we didn't get 7. We get t equals 9. So in the end, it didn't work. Right? It didn't work. Therefore, the point is not on line. We needed to get the same value for t in all 3 spots. It does tell us that there is a point on the line that goes 7, 5 something, right? If t is 7, then the 7 and the 5, or excuse me, the 15 and the 9 will appear. We will get that 15 and the 9, but you're not going to get the minus 6. Okay, so for it to be a point on the line, all 3 of those have to check out. Keep in mind, if we checked, say, x and z first and got the 7 and the 9 right away, we'd know immediately that it didn't work. You wouldn't have to check the third one. All right, a couple of problems we need to try. Show that the lines are parallel. In two-dimensional stuff, when we do y equals mx plus b, if you want to know the lines are parallel, you just consider the slope. And if the slope is the same, or multiples of each other, I guess, then they're parallel. And same thing here. The initial vector, that 2, 3, 5, and the 15 minus 12, 20 make absolutely no difference to whether or not lines are parallel or not. What's important is that we consider the direction vectors. Now, I want you to notice one other thing up there. Line 1, I have t as the parameter, and line 2, I've written the parameter as r. I had to do that. I can't use the same parameter twice because I'm not trying to say, what I don't want to say is if t is 2, I don't want t to have to be 2 for both the first line and the second line. So I can use 2 different parameters. I need to use it like that. So are these parallel? Well, I need to consider the 2 direction vectors. So the direction vector of the first line, I write that as d1. So we had line 1, right? And then I have d1, direction vector of the first line, is minus 3, 2, 6. And d2 is 6, minus 4, minus 12. And so are those actually multiples of each other? They are. Right, if we take the first vector and multiply it by negative 2, we get the second vector. So the way I can write that, I can say minus 2 d1s is equal to d2. Therefore, the lines are parallel. I'm going to put a little question mark after that because of what I've got at the bottom there. Maybe you didn't see it. It says, have you thought of everything? We almost have. We've come really close. We've done good stuff. We know that the direction vectors are parallel. Is there any other possibility? And so think back to grade 9 again, maybe even grade 10. If we're considering the possibilities of 2 lines, things that 2 lines might do, they might be parallel, they might intersect, and the third possibility, the one that hardly ever came up, was maybe they're actually exactly the same line, right? Maybe they're the same. For example, if I gave you this one in grade 9, y equals 1/2 x plus 4, and y equals 2 over 4x plus 4, right? Those are the same line. So not only are they're not just parallel, they're the same. The other way we did that was something like this. 2x plus 3y equals 5. And then if I just had a multiple of it, those turned out to be turned out to be exactly the same. So that was the grade 9 and 10 equivalent. How do we know now? We have these 2 different lines, well, maybe 2 different lines, I should say. How can we check to see if they're the same or not? Well, if they were the same, then they share every single point, right? Every point that's on line 1 is also on line 2. So that means this point right here, 15 minus 12, 20, it's definitely on line 2. If it's also on line 1, then we must have the same line, right? I know now if the direction vectors are multiples of each other, I know that the 2 lines are either parallel or the same. So now I'm just checking to see if they're the same. So I'm going to check is the point 15 minus 1220 on line 1? Is it on the first one? And we just did that question, right? We checked to see if things were on lines. So what you need, excuse me, you need the parametric equations. 2 minus 3t you could have done this the other way around too, I suppose, right? Could have subbed 2, 3, 5 into line 2. 15. This doesn't look very promising based on, I'm actually going to do that one. What do we get? 13 divided by minus 3. It's a pretty ugly number for t. And that's minus 15 over 2 equals t. So I don't even need to consider the third one, right? I got different values of t. So I can say, therefore, the point isn't on the line. And since that point isn't on the line, that means these two lines must be different. And we already knew they were going to be parallel then. Lines are different, they're not the same line, and they're parallel to each other. So not bad. One of those ones where you don't think there's more to consider, and in fact there was. This one can be a long one. It says determine the point of intersection, if any, of the lines. So there's two lines given. Notice I gave them to you right away in parametric form. I didn't need to do that, just saves us a step. So we did parametric form. Notice I've got the t and the r, so I've got the different values again. We're trying to find the point of intersection, and it says if any. So one of the things I need you to think about, go back to 2 dimensions for a second. If I said find the point of intersection of two lines in 2 dimensions, the only way that there isn't a point of intersection is if the two lines are parallel. But in 3-dimensional space, you can check this pretty easily. If you just, again, hold up 2 pencils, those are representing the lines. If you hold them up and sort of orient them in some funky way, what are the chances that they actually cross? And it's very slim. Right? I mean, a line takes up such a little amount of space in a 3D world. So the chances, if I were to randomly pick 2 lines of them actually intersecting, would be very, very small. Of course, I'm not picking things randomly necessarily, right? I want to see if we can do the math on it. But if we were randomly picking 2 lines, they probably don't intersect. So as we check this, we have to be able to go through it and say, well, if there is a point of intersection, let's find it. And if there isn't, we have to make sure that we understand why there isn't one. We have to do a lot of algebra in this unit, a lot of substitution and elimination, like you would have done back in grade 10. So if you're feeling a little rusty on that, that's something that you should check a little bit on. You'll need it. We're going to do quite a bit of it in the next little while. The way we did this type of question in grade 10, we had substitution and elimination, right? If you were, let me even scribble one again for a second. If I had x plus y equals 10, and then you had, say, y equals 2x plus 4. I'm not going to finish it, but there's some question. One of the ways that we could solve it was by substitution. And we'd say, hey, y is equal to 2x plus 4. I can substitute that in for y and then solve the equation. And that worked pretty well because you're getting rid of variables. And that's what we need to do. The reason it worked, the reason we were allowed to make that substitution, is we're saying if there was a point of intersection, those two y values would have to be equal. And that's the key here too, is if we're finding a point of intersection, the x value in line 1 has to equal the x value in line 2. The y value in line 1 has to equal the y value in L2. So I can take all of these equations and pair them up. I'm going to put all of them together. So our first equation is going to be 5 plus t, this is from the x's, is equal to minus 9 minus 4r. That's our first equation. Second equation is 2 plus 4t equals 9 plus 5r. And the third one, minus 1 minus 3t equals 2 minus r. Now we've done some neat stuff already. We started with 2 lines. We had variables x, y, and z, and t and r. So we started with 6 equations and 5 variables. And really just in one step, we've compressed that now to 3 equations and 2 variables. So we've simplified things a lot in a very quick time. The thing I need you to remember now, though, it makes a difference how many variables and how many equations we have. So I'm going to scribble again on the side. When you're in grade 9 and you learn something like this, 2x plus 5 equals 11, we were able to solve that equation because it was one equation and had one variable in it, right? And then we got to grade 10 and we said, well, if I put a y there, now I can't solve that anymore. Now I need a second equation in order to solve it. So if I have 2 variables, I need 2 equations. If I was going to have 3 variables, I would need 3 equations. If I had 4 variables, I'd need 4 equations, and so on. Well, this is now backwards, right? I've got 2 variables. I only need 2 equations to solve. I only need 2 of them. The third one's a bonus. So what I'm going to do is I'm just going to pick 2 of these equations and try and solve those. And I'll show you what I mean. I'm not for any reason other than I think it's going to be easier for me to write. I'm just going to pick those top 2, okay? The third equation might have actually been easier, but just for space on the board, I'm going to try these 2. I'm going to rearrange them so that it looks a little bit more like, well, honestly, so it looks like elimination, because elimination is going to be the way we're going to want to handle a lot of the questions here. So substitution is good, elimination is going to be better in a lot of cases. So I'm rearranging the first equation. I'm going to leave the t on the left. I'm going to bring that 4r over, and I'm going to bring the 5 over to the other side. You do the same thing for the other equation. So the 4t is there. Bring the 5r over, and subtract 2. So that gives me those ones. I think I need to shorten this up just a little bit. So I've taken the 2 equations, just rearranged them so that they look a little bit better from an elimination standpoint. Now with elimination, what we're trying to do is we're trying to get the coefficients to be the same. So when we eliminate, when we add or subtract the equation, something's going to cancel. Nothing's set up at the moment to cancel perfectly, but it'll be relatively easy for me to multiply this first equation by 4, and then all of the t's are going to be the same. So I multiply that by 4. 4t 16r minus 60, equals minus 60. And then the bottom one I'm not changing. I want to leave it as the 4t. And so now I've got the 4t's in both the first and the second equation. So I'm going to subtract the 2 equations. So 4t take away 4t is 0. Those are gone. 16 take away minus 5 would be a 21r. And minus 60 minus 7 is going to be a minus 67, which looks really ugly. That makes me think I did something wrong. What did I do wrong? Oh, I added really badly on the red one, didn't I? This is hard teaching it in front of you guys when no one actually can correct this. So I don't know if you guys spotted it. That minus 15 in the red there was wrong. Minus 9 take away 4 is very rarely minus 15. Should have been minus 14. And how does that fix things then? I hope so. Minus 14 times 4 would be minus 56. That looks better. And now when I subtract, there we go. Now when I subtract, I get minus 63. I was worried I was going to do something like that. And now I get r equals minus 3. That sounds a lot better. Pretty good lesson really for you guys too. When you're doing, hard to say with the homework, textbook can be mean, right? Sometimes they give some ugly answers. If you're doing a question with me on a test and you got an answer of whatever, what was I going to get there? Minus 67 over 21. Chances are that's wrong, right? I'm just not going to give you that on the test. Very rarely. Assignment, maybe, but even then I'm being pretty mean. So if you start getting ugly numbers, you've probably messed up somewhere. And it's so easy to do. I mean, I added minus 9 and minus 5. I got minus 15. That's about as bad a mistake as you can make. So just be careful. And if you start seeing numbers that look funky, take a look back and see if you can find the problem. Okay. Remembering what we were trying to do then. We took equation 1 and equation 2, and I'm trying to solve for r and for t. So I've got r equals minus 3 now. I'm going to sub that into that first red equation, so into equation number 1, which was t plus 4r equals minus 14. Now it actually got that right. So if I sub that in, I'm going to try and solve for t. What do we get there? Minus 12, so add 12, t is minus 2. So we've done well. We've managed to solve the system of equations that had equation 1 and equation 2 in it. So basically what that's telling you then is we found r and t. And if you look back at what we started with, we had line 1 and line 2. That would give us the two parameters, gives us r and t. We were trying to find the point of intersection, right? So have we done it? If the point of intersection happens when r is minus 3 and t is minus 2, we almost have. There's one extra step, and the issue was what I said before. The chances of actually having a point of intersection should be very small, right? There probably isn't one. But if you think about what we just did, the calculations that we just did, we ignored equation 3, right? We only used equation 1 and equation 2, which means really we did a problem in 2 dimensions, right? We did a grade 10 problem. Pretend the t and the r were x and y. We had 2 variables and 2 equations. And in grade 10, you pretty much always get an answer when you do that. Right? If 2 equations and 2 variables, you should always get an answer. So of course we got an answer. We got r equals minus 3 and t equals minus 2. That makes sense. Right? We should have gotten an answer from that. But if we can always get an answer by doing that, and we shouldn't always have a point of intersection, there must be something else that happens. And that something else is the equation 3 part. What we need to do is we need to get values of t and r that work not just for equation 1 and equation 2, but also for equation 3. So all that we've guaranteed so far is that r is minus 3 and t is minus 2 works for equation number 1 and equation number 2. I still need to check to verify that it works in equation 3 as well. So that is our final step. It says verify that r equals minus 3 and t equals minus 2 is a solution to equation 3. And so all we're going to do for that is we're going to sub it in on the left side and the right hand side of the statement. So the left hand side was minus 1 minus 3t. I'm doing a left side, right side because I'm checking it, right? I'm trying to see if it's actually correct or not. Minus 1 minus 3 times minus 2. So that's 5. And 2 minus 3, that's 5. So that's great news. That means that our solution actually does work in equation 3. So because of that, we can say, therefore, there really is a point of intersection. So we're in that incredibly rare, should never happen unless I made up the numbers just right so that it would work sort of scenario. And that's what happened, of course, right? I picked the numbers so that we'd get a point of intersection. If it had happened that our left side didn't equal the right side there, then we'd be done. Our therefore statement would say, since the left side didn't equal the right side, excuse me, all 3 equations are not satisfied, therefore there is no point of intersection. This time, since there is a point of intersection, we need to find it. It's easy to find it. We just go back up to those parametric equations that we have, and you can pick either L1 or L2, and we're just going to sub in our numbers. I'm just going to grab line 1 there. So 5 plus we're going to sub in the t value of -2. And that'll give us the point 3. I'm really worried that I'm going to make calculation errors after that. Bungle with the 9 and the 5. That's a 5 there. I'm really short on space. Let's get this guy out of there. So therefore the POI is 3 minus 6 and 5. So we get our point of intersection. That's a long question. There's a lot of algebra there. And that check at the end is the part that gets forgotten the most. So maybe put some sort of a star here or something. People usually do very well on this question on the test. It's always there. But sometimes that checking in the third equation gets forgotten, and it's such an important part. It's just got to be there. Okay, we got one more. It says determine if the line has any x, y, or z intercepts. So does it have any x, y, or z intercepts? If it has an intercept, because we're talking like intersecting an axis here, right? If we needed something to intersect the x-axis in 2 dimensions, then we needed the y value to be 0. Right? That was how we found x and y intercepts. If we wanted to find the x-intercept, we set y to 0. If we want to find the y-intercept, we set x to 0. Well, now you've got 3. You got x, y, and z. So if there was an x-intercept, then y has to be 0 for sure. But now z has to be 0 as well. You need both. And that's the added part now that we're in 3 dimensions. So the only way we can get an x-intercept is if y is 0 and z is 0. So let's check. Let's see if we can make that happen. That means, can we find a value of t that's going to give a y value of 0 and also give a z value of 0 at the same time? So I'm going to write the parametric equations out again. Remember, everything's with parametric, right? Y is 1 plus t. Z is -2 minus 5t. And I'm going to sub in 0 for y and 0 for z. And this, fortunately, this is going to solve a little bit quicker than the last example we did. We get t is -1. So if t is -1, then we're going to get a y value of 0. But for z, that's not going to work. For z, if we want to get a 0 there, the parameter had to be -2/5. So they weren't equal. So our conclusion is that there is no x-intercept. And that's pretty reasonable, right? It's the same idea as the point of intersection part. You're talking about the x-axis and a line. So if I randomly put a line in a 3-dimensional space, it probably doesn't touch the x-axis. It might, it's possible, but randomly picking a line, it probably won't. All we've done there is said there's no x-intercept. If we want to find it, if there's a y-intercept, I need a new color, there we go. If there was a y-intercept, then I would need x to be 0 and z to be 0. So same idea, right? Now I'm checking x and z instead of that first part where I checked y and z. Well, I've already done the z part, right? I've already subbed in a 0. I know that I need to get -2/5. I just need to check x now. So I'll sub in the 0 for x and solve for t. And I get -4/3 on that one. So to get a 0, to get a y-intercept, I can't get that either, because to get 0s for x and z, I need different values of the parameter. So this doesn't work. I'm going to make a mess of things. I'm going to do it anyway. So I'm pointing at this guy and this guy. And because they're different, there's no y-intercept. And hopefully you're already a step ahead of me now. If we wanted to check the z-intercept, to get a z-intercept, we would need x and y to be 0. Well, we've already done that too, right? We've got the values of t. If we subbed in 0 for x and y, we get minus 4/3 and minus 1. That didn't work either. So there's also no z-intercept. Okay. So we had to, what I'm trying to show you is how much we're using the parametric equations. Right? We're using them for so many of these calculations. Everything depends on what the value of t will be. The value of t generates points. And so to get particular numbers in the point, in the coordinates, if I want to get a 0, these are the numbers that I have to sub in for t. But because they're all different, I'm never able to get more than 1 0 in the point at a time. But as I said, that's not a surprise, right? Randomly pick a line, it probably doesn't have any x-intercepts. So we're not too surprised by that. So there you go, that's covered. Now we've done lines in 2 dimensions and we've done lines in 3 dimensions. Biggest question on this one was that finding a point of intersection. Right? That's I think in your textbook actually it's a whole section. So we've sort of put it in together here. It's a big question. There's a lot to consider, a lot of algebra there. And remember, as I said, we're about to move into planes. And pretty soon we're going to be finding more intersections. We're going to be intersections of planes. And when we get there, the algebra, well, I mean, again, I screwed it up already, right? If you're not remembering substitution and elimination very well, you're going to want to take a look back and just look that up for 5 minutes. Just remind yourself a little bit about how substitution and elimination worked.